Hi, I'm Laia Blavi, and I'm a postdoc researcher in the Stein Monogastric Nutrition Laboratory of the University of Illinois. And today, I will be talking about the effects of zinc oxide and microbial phytase on the digestibility of calcium and phosphorus in mice-based diets fed to growing pigs. For this presentation, I will start by giving a brief introduction on the nutritional requirements for minerals in the weanling pigs, and also I will talk about the mineral interaction. And then I will move to the materials and methods, and then dive into the results and discussion for this experiment, before drawing conclusions and then giving a take-home message. The nutritional requirements for calcium of a pig between 11 to 25 kilograms are 0.70%. The problem is that swine diets are based on plant sources that have low calcium concentration, and therefore we have to supplement them with inorganic sources like calcium carbonate or animal sources like meat or bone meal. The nutritional requirements for zinc are around 100 ppm, but it can be used therapeutically up to as much as 3,000 ppm of zinc oxide to prevent the post-weaning diarrhea and to promote growth performance. So often, we are adding high levels of zinc and calcium to post-weaning diets, but zinc and calcium show an antagonistic interaction, meaning that they inhibit the absorption of each other. This is because they are chemically similar and share similar absorption mechanisms. It has been observed that zinc can compete with calcium for absorption through channeled proteins on the brush border membrane in the small intestine. And also, zinc and phosphorus show an antagonist interaction. Therefore, it is possible that elevated levels of dietary zinc can interfere with the absorption of calcium and phosphorus. We also have to take into consideration that piglets have low acid secretion, and after weaning, the diets contain low levels of lactose. That is the principal source of acidity by bacterial fermentation. Moreover, diets contain calcium carbonate and zinc oxide have higher acid binding capacity, also called buffering capacity. That is the ability to neutralize any feed acidity. Taking all this together, increases in the digestive pH can decrease the phytate solubility and also the activity of phytase. Calcium and zinc might bind to phytate, which can decrease calcium absorption. However, nowadays we can use phytase, an enzyme that hydrolyzes the phosphormonoester bonds of phytate, and thus might increase the digestibility of phosphorus and calcium. However, possible interactions between zinc and phytase on the standardized total tract digestibility of calcium have not been reported. So, the hypothesis of this experiment was to test if pharmacological levels of zinc affects apparent total tract digestibility of calcium and phosphorus and standardized total tract digestibility of calcium, and whether microbial phytase increases the ATTD and STTD of calcium and the ATTD of phosphorus regardless of the concentration of zinc in the diet. A total of 56 growing barrows between 50 to 20 kilograms were allotted to a randomized complete block design. We used 7 diets, so we had 8 replicates per diet. One diet was the diet free of calcium to determine the basal endogenous losses of calcium, and the other 6 diets were the dietary treatments. That followed a 3/2 factorial, where the main factors were phytase and zinc. The levels of phytase were 0, 1000, or 3000 FTU of phytase, and the levels of zinc were 0 or 3000 ppm of zinc oxide. The phytase that we used for the experiment was Quantum Blue of AB Vista. The total experiment lasted 13 days, where the first 5 days were the adaptation period to adapt the piglets to the diet and to the metabolic cages. The diet was offered to the pigs twice a day. On day 6, the first marker, indigo carmine, was added to the diets, and for 5 consecutive days, the feces, urine, and the orts were collected. We started to collect the feces when they turned blue. At day 11, We added the second marker, ferric oxide, and we collected phytase until red appeared. The experimental diets were based on corn. In this table, we can see how calcium-free diet had no calcium carbonate addition, and the diets with therapeutic levels of zinc had 0.3% of zinc oxide. For the analyzed composition, the calcium-free diet had negligible traces of calcium. Zinc, phosphorus, and phytase values were in agreement with the calculated values. Moving to the results, I will start with calcium. All the following results slides will have the same format. In this graphic, we have the apparent total tract digestibility of calcium. On the x-axis, there are the 6 dietary treatments. The first 3 bars, the orange ones, are the diets without zinc oxide addition, and the last 3, the blue ones, are the diets with zinc oxide. In each group of diets with zinc oxide or without zinc oxide, there are the 3 levels of phytase, 0, 1000, and 3000 FTU of phytase. The y-axis represents the percentage of apparent total tract digestibility of calcium. The ITTD of calcium increased as the concentration of phytase increased, as signified by the pink arrows. But it was lower when zinc oxide was added to the diets than when not zinc oxide was added. The red arrow represents the mean ITTD of calcium without zinc oxide and with zinc oxide. The standardized total tract digestibility followed the same pattern as ATTD, where the digestibility increased as the concentration of phytase increased, and it was lower when zinc oxide was used than when not zinc oxide was added. Calcium retention takes into account the urine losses of calcium. Pigs fed the diets with 3000 FTU and without zinc oxide had greater calcium retention than pigs fed the diets with 1000 FTU and without zinc oxide. However, in pigs fed the diets with zinc oxide, there were no differences between the addition of 3000 and 1000 FTU of phytase. The percentage of apparent total tract digestibility of phosphorus increased as the concentration of phytase increased in the diets, represented by the pink arrow. But it was lower when zinc oxide was added into the diets than when no zinc oxide was added. The results of phosphorus retention, which takes into account the urine phosphorus losses, also followed the same pattern. The percentage of phosphorus retention increased as the concentration of phytase increased in the diets. We can see in this graphic that the bars with 3000 FTU were greater than the bars with 1000 FTU. But this increase was lower when zinc oxide was added into the diet. So, to conclude, pharmacological levels of zinc in the diets reduce calcium and phosphorus digestibility, but the addition of 1000 FTU of microbial phytase ameliorates this negative impact. And 1000 FTU of microbial phytase increases the ATTD and STTD of calcium and the ATTD of phosphorus. Finally, the take-home message of this presentation is that if pigs require pharmacological levels of zinc, we can either increase dietary concentration of calcium and phosphorus, or we can supplement the diets with phytase. And with that, I would like to thank my fellow lab members. Without their help, this experiment would not have been possible. If you enjoyed this presentation and you would like to know more about this topic or want to learn more about nutrition, you can visit our website at nutrition.ansci.illinois.edu. Thank you for your attention.